Ok, buongiorno a tutti. Direi che possiamo iniziare con questa prima sessione dedicata ai recenti sviluppi, alle prospettive nel campo della meccanica e dell'ingegneria delle rocce, che è l'eredità che ci ha lasciato il professor Barla a tutti noi. I switch to English now just to introduce our international guest, Professor Jean Sulem. Jean Sulem is professor at the Ecole nationale des Ponts et Chaussées in Paris. He's also director of the Laboratoire Navier. His contribution in the field of rock mechanics are well known and includes the works on bifurcation theory, on which I studied very much during my PhD, and many other works on the geomechanical modeling of geomaterials and experimental rock mechanics and many other fundamental works. In this presentation, he will talk to us about the recent development and perspective in the field of rock mechanics.
Thank you, Marta, for the kind introduction. Good morning. I would like to thank Marco Barla for the invitation to participate to these days, this tribute to Giovanni Barla. I'm glad to be here to participate as a rock mechanician and also this afternoon as a musician. As you know, we can say much more with the music than with the words to express my long-standing friendship with Giovanni Barla. I had the chance to meet Giovanni in the late 80s, and since then we have developed long-standing cooperation. Giovanni was very active in developing academic links between the Politecnico di Torino and the Ecole des Ponts, building the double diploma in engineering and also double diploma in PhD degree. And we had many exchange of students. He was coming often at the school to evaluate the works of our students, and also we had supervised together a number of PhD students. So I am glad to be here today. When Marco invited me, we proposed this title, Future Trends in Rock Mechanics, which indeed is quite a challenging topic, which obviously cannot be treated in a single talk. So I've made some choices of topics that I will discuss this morning. First, as an introduction, I will emphasize some new challenges in rock mechanics, especially in relation with energy transition and climate changes. And then show some advances in experimental rock mechanics, especially linked to combination of experiments and imaging in order to explore the physical processes. And then I will move to another topic, modeling cracking in rocks, as we have many papers published in this domain, mainly inspired by the developments in the domain of the mechanics of brittle materials. And I will try to show the advantages, but also the limits and the future of these methods. And if I have time, I will address the last topic about multi-physics phenomena, multi-scale modeling. We know that physical processes occur at various scales. And so when we address multi-physics problems, we have to treat them considering the different scales and how a physical process at one scale can influence another at a different scale. So concerning the new challenges in rock mechanics, energy transition towards renewable energy, we know the importance of developing a geothermal system in order to reduce the use of hydrocarbons. The main challenges is about the performance, the economic viability, the safety, especially the induced seismicity and the acceptability of the population. Also, we know that these renewable energy are often intermittent, like wind energy, solar energy, so it's necessary to develop a system for storage, and hydrogen is a vector for this storage, also to reduce the impact of greenhouse gases, the necessity to store CO2, and also in France and in other countries, there is a main topic about nuclear waste sequestration, where the question of long-term tightness is, of course, a major topic. And the topics related to climate change, and we have heard also the recent news, how the hazards can be really catastrophic. The problems of drying, resaturation cycles in rocks, or impact of freeze and thaw cycles on rock weathering, and the implications for rock slope stability, embankments, rock falls, rock avalanches, landslides. Again, there are many papers published in this domain in the recent years. So we know that it's not possible just to extrapolate the experimental data that we have a small-scale sample and short-term experiments to very long-term or field situations. So it's important to explore, understand, and model the involved physical-mechanical processes for reliable large-scale and or long-term predictions. Let's say a word about this multi-physics phenomena we address in rock mechanics. First, the mechanical processes, the processes involving damage, fracturing, cracks, growth, healing. Also, multi-phase fluid flow, the effect of temperature, of chemical reaction, or biochemical reaction. Also, microbial reactions, for example, for H2 storage, the effect of the bacteria that will consume the H2 is a key issue. Also, bacteria have some effect in producing additional gas, and it plays a role in the stability of some faults. And as I said before, we have to consider the combination of the various processes. We know, for example, that chemical reaction or dissolution will affect the stability or the strength of the material. So we are dealing with multi-physics couplings. And these different processes occur with different time scale. And we have, in the engineering problem, identify what is the relevant time scale of the problem, which can be very different, hours or days for laboratory experiments, but in civil engineering structures, we have to design for tens of years. When we deal with nuclear waste storage, we speak about thousands or tens of thousands of years. And for example, for seismic activity, we have to handle different time scales, hundreds of years for the seismic cycle, but only a few seconds for earthquake. And addressing multi-physics problems, as I said before, necessitate to look at the proper scale and see how the various scales interact one with another. We know that rocks are heterogeneous at all scales, from grains, pores, microcracks, to larger features, fractures, joints, or faults. We have to understand the processes of rock deformation, damage at the grain scale. Various phenomena can be involved: breakage of intergranular bonds, abrasion, breaking, crushing of grains, frictional intergranular sliding, rotation of grains, growth of microcracks, and dilatancy. Chemical interaction between reactive pore fluids and minerals, such as dissolution or precipitation or swelling in clayey rocks. They occur at some micron scale, but they affect the fluid flow at much larger scale, which is the porous network of the fractures themselves. So often for engineering problem, we have to work at the macro scale. This is to develop constitutive modeling for equivalent homogenized continuum. This is a challenging problem of upscaling that we have to address, and the description, explicit description of macro discontinuities. And all these processes interact. After this global context introduction, I will give some hints about some recent work we have done in our group about combining experiments and imaging in order to explore the deformation mechanisms of rocks from small scale to the macroscopic response. And this is a work done on a highly porous carbonate rock to understand how the porosity heterogeneity controls strain localization. So combining triaxial testing, X-ray computed tomography, it's possible to build through digital volume correlation 3D strain maps and also porosity maps. The particular rock we were interested here is a limestone with high porosity from the Paris Basin, Saint-Maximin limestone. The porosity is high, 38%, mostly calcite and 20% of quartz. And we see here a micro SEM image where we see the complexity and the heterogeneity of the microstructure with various scales of porosity, the macropores with a size of typical few hundred microns, but also the mesopores with a few tenths of microns, and the calcite grains are themselves porous with a pore size below 1 micron. We identify also this quartz grain in darker gray here in this image. So from the X-ray computed tomography image, we could build the porosity map. We see that it's quite heterogeneous, ranging from 25 to 55%, in red the most porous zone, and we'll see also this alternation of more porous, or in blue, the less porous zones, and quite with a typical length scale of alternation of about 1 or 2 centimeters. So in terms of the classical response, we identify the brittle response here at a low confining pressure of 1 MPa with the inclined shear bands, and the transition from ductile to brittle is at 6 MPa of confining pressure, and at 11 MPa we see this ductile response with the formation here of subhorizontal deformation bands, which we identify as compaction bands. Also, if we build the strain maps at various levels of loading, we see here the zones where the volumetric strain is localized, either in incline or subhorizontal bands, and at further higher loading stage, we see how these bands enlarge, develop, and progressively fill the sample. What is interesting to notice is that actually this is the porosity map, this is the volumetric strain map. The zones in blue, which are the less porous ones, almost have no deformation. All deformation concentrates in the zones of higher porosity. This is what we see here also. So at the scale, this is the scale of the sample, which represents the representative elementary volume. We have to account for this heterogeneity in a model which is typically non-local. This is what can be done. So without going in detail in the equations, just saying that we have here a second gradient plasticity model, which is adequate to describe this non-local aspect of the deformation process. We take into account not only the mean porosity in the yield surface, but also its second gradient. We know that this type of enrichment of the kinematics is necessary when we treat strain localization problem in order to give material length to the problem. What is interesting here, it is not a purely numerical or mathematical trick. It's based on physical observation, because all the additional quantities that come from the second gradient model, this is the internal length, or also the hardening laws, how the yield surface evolves with the porosity and also its second gradient, comes from the porosity and DVC maps that we do. So from the observation at a small scale. Also the internal length comes from the dominant wavelength of the porosity heterogeneity, which gives the size of the representative elementary volume. As an example, this is how one can implement such a model in a finite element code in order to have a robust modeling of compaction banding, and with good comparison of numerical and experimental observation, both for the onset of, for the plastic volumetric strain inside the band at various stages, but also for the thickness. Of course, the thickness is an important parameter when we deal with change in permeability. And now we went a little further in this work, because we went to the Soleil synchrotron in the south of Paris, and by coring small samples inside the low porosity zone or the high porosity zone, this is the type of image we have with the resolution of 2 microns, we see that the low porosity zone is more heterogeneous and the high porosity zone is more homogeneous. And the resolution is good enough so that we can identify the various mechanisms like pore collapse, grain crushing, or intergranular cracking, as we see here. And so in this device, we could put it inside the synchrotron, so we do the image without unloading. And you see all this small stress drop correspond to the time where the image are done, going up to 15 or 20% of deformation. We identify for the more denser sample at low confining pressure this brittle with the peak behavior, whereas for the porous, it's only ductile. And if we draw the yield surface, we see that the porous sample fail at lower stresses than the denser sample. Also, so this is a type of image analysis we do. So from this image, we build here the volumetric end shear strain for the porous sample and for the dense sample. So at low confining pressure, we see the formation of these inclined shear bands. And for the dense sample, we see in blue that we have first dilatant shear band or opening of microcracks, and later compaction, whereas in the porous sample, we have mostly compaction, which start here in the zone of more porous material. Also, if we look at the evolution of the porosity, this is the porosity profile of the sample. So we see here a zone of a higher porosity, and this is how it evolves in the due course of the loading. So we see that first we have homogenization of the porosity, and at this stage the porosity is almost homogeneous, and then we have homogeneous compaction of the whole sample. This is represented here. So this is the volumetric strain as a function of the initial porosity. So at the beginning, the zones of low porosity first have some dilatancy, so some cracking, and then, whereas the zone of higher porosity have only compaction. And you see this evolution, and at some point, the whole graph is moving, translating, which corresponds to this uniform compaction. So we have strain which localize first in the most porous zones, and then diffuses and fill the whole sample. And we have the densification of the sample and the homogenization of the porosity. This is a work that has been performed in a PhD thesis of my student, Catherine Doré-Ossipian. She will defend the thesis in 2 weeks in Paris. Modeling cracking of rocks, and just to have a brief overview of numerical fracture models for modeling rock breakage mechanisms and crack propagation, coalescence, we generally distinguish between what is called weak discontinuity and strong discontinuity. Weak discontinuity consists in considering the cracks as the bands of strain localization. So they are weak in that sense that the displacement field is continuous, only the deformation field is discontinuous. So it's not a material discontinuity. The material is continuous, and such an approach, I will give an example, was developed, for example, in the study of the damage zone, which is forming when excavating galleries, tunnels in clayey rocks. As you probably know, in France, there is a project of storing the nuclear waste in the east part of Paris, in Bure, in a clayey formation, Calovo-Oxfordian clay, at 500 meter depth. And for that, there is ANDRA, which is the national French agency for nuclear waste, which has established a laboratory, underground laboratory, for more than 20 years with many experiments. And what is observed is that when excavating inside this clayey rock, there is a zone, a damage zone, induced fractures by the excavation with different pattern, geometry, extension, depending on the orientation of the gallery with respect to the principal stresses. So there's been lots of publication about the modeling of this fracture pattern, and I mentioned here one recent work done by the team in UPC in Barcelona, where they could simulate numerically the fractured zones in terms of shear strain contours, and they could reproduce correctly what is observed in the field for both direction of excavation and extension of the zone. So the work is the finite element modeling of strain localization, onset and propagation of the shear bands. They could account for multiphasic coupling, desaturation due to excavation and ventilation, and then resaturation. Also thermal effects due to the presence of the waste later could be introduced. In particular, the effect of thermal pressurization of the pore fluid in the clayey rock. And they could model the evolution in time of deformation of the pore pressures in the rock. But we know, as I said before, that when we deal with strain localization, we have to regularize the strain localization problem. Here they have used non-local damage model, higher order gradient models. However, in this study, this is more a numerical regularization because the internal length is not related to the microstructure of the material. We know that although the results are interesting, it's more an academic work because it's at high computational cost, difficult to compute long-term evolution, and the constitutive behavior of the material at very highly strained zones is still poorly known. So this type of model, although interesting, is difficult to implement in design tools for engineering practice. The other type of approach is what is called strong discontinuity approach. So there we model explicitly the cracks as a discontinuity and discontinuity of the displacement field. And again, here we've distinguished between what is called sharp crack models, where the displacement field is discontinuous across the crack, and diffuse crack models, where we consider the continuity of the displacement, but with very high gradient along the crack path. And then, this is the case here, the smeared crack, where an internal length is introduced. So this might look like what I've shown before in terms of strain localization, although this is a purely numerical model, not based on the physics. But we still see some correspondence, especially the use with the gradient theory. And I could recommend an interesting work of Nicolas Mouès in a recent course that was given, and this is online book, where he discuss how to take the best of both worlds, the advantage of the sharp crack models and the advantage of the diffuse crack models. So for the sharp cracks, historically, first we had the finite element methods based on fracture mechanics, but we know the difficulty to handle large deformation, tortuous fracture patterns, branching, coalescence, and the necessity to refine the mesh at the crack tips, and the necessity for frequent remeshing as cracks advance. It's done at high computational cost. We can treat limited number of cracks, and it's sensitive to mesh orientation. So later there was also inspired by the developments in the mechanics of brittle material, what is called extended finite element method, where the shape function are enriched with discontinuous displacement field. So this has an advantage that the cracks can propagate along arbitrary paths, and there's no need for remeshing. Still, there are some limitations limited to linear elastic fracture mechanics, difficulty to handle branching and coalescence, and it's also limited to treat a small number of cracks. Boundary element methods, many papers on this, but we had to know the crack path, and again, the number of cracks is limited. For the diffuse smeared crack models, a very popular approach, phase field models, as introduced by Frank Faure and Marigot, which see many papers now in rock mechanics. So the crack propagation is based on energetic arguments, the competition between elastic potential energy and fracture dissipation, without ad hoc crack propagation criterion. We have seen application in many different physical contexts: hydraulic fracturing, heterogeneous materials, ductile behavior, finite deformation, multi-physics couplings. It can master crack nucleation, growth, branching, coalescence, complex crack growth, and networks of cracks. So a lot of advances are compared to the previous methods I have shown. The drawback is that we need to use very small elements along the crack to represent the high gradients, and then a very high number of elements, so it's very high at very high computational costs. One word about mesh-free methods, which are continuum methods. Smooth particle hydrodynamics, which is used in many domains and also in the domain of modeling cracking. And there, the discretization of the domain is done in two particles that represent specific material volumes that interact with each other via some kernel approximation. It's a true Lagrangian approach, and the particles follow the deformation and the flow. It can handle large deformation, discontinuity, fragmentation, impact, collision, fractures, many aspects. But it's difficult to calibrate. It's difficult to assign properly the boundary conditions to assess the relevant number of particles, and the physical meaning of the interaction model is not obvious, and it's applied mostly to small size problems. And along the same line of thoughts, material point model, again, very popular now in some recent papers. It's also a Lagrangian approach, can handle large and discontinuous deformation, can simulate rock cracking, and the boundary conditions are much better controlled. And, but we see that all these models are computationally expensive and present numerical difficulties. To go quickly, I mentioned discontinuous methods, which are very well known, but more recently, what we see is to combine these methods in what is called hybrid models for multi-scale analysis. So at one scale, we will use DM, for example, and at higher scale, we'll use finite element. But the main limitations here in the computations is the necessity of this microscopic simulation, which leads to the next slide, which is how machine learning tools can be used for rock modeling. We know that artificial intelligence, machine learning is used in many domains of our life, and also in research and in rock engineering. What I want to show here is how we can go beyond the limit of multi-scale modeling with hybrid model, which is very time-consuming because of the computations we have at a small scale. So the idea here is to train, here it's an artificial neural network, to train this network, to be able to replace the computation at a small scales by the machine learning tool. As for example, the input layer is the state of stress and deformation, and for a given increment of stress, we can obtain the corresponding increment of stress. And I mentioned here an interesting work of Filippo Masi and Yannis Stefanou. You know that all these machine learning tools must be based on some physics, and they show how to introduce some thermodynamics laws, because if we replace the constitutive models by the trained models, for example, they have to respect the fact that dissipation should be positive. So this is one aspect of taking into account the thermodynamic law. If I have 3 more minutes, I will go quickly to the last topic of multiphysics phenomena, multi-scale modeling. What I want to emphasize here is how it's necessary to handle some problems when we have different physical processes to handle the problem at different scale. The example I give here is the combined effect of dissolution and grain crashing. We know that the dissolution is enhanced if the area of contact between the reactive fluid and the grains is larger. So we know that dissolution is more active in damaged zones of the rock than in intact rocks. So the acceleration of the dissolution will produce some chemical softening, because we know that if we have dissolution, the strength of the material will be reduced. So with a strength which is reduced, we will facilitate damage or grain crashing. So in due course of this phenomena, we will increase the specific area of the grains, and you see that we have here this loop with positive feedback for which one can question the instability. This was addressed in some papers some years ago, but I just wanted to emphasize the approach. And to explain the distinction of the scale, so schematically here, this is the representative elementary volume with some heterogeneity of the microstructure. For example, the grains, the different grain level indicates this heterogeneity. So at the elementary volume scale, we write the macro scale, we write the constitutive equations, the momentum balance, the mass balance. But when we have to describe the reaction kinetics or the grain crashing of the solid skeleton, we have to write the model at a small scale, so at the scale of the grain. So let's take this example, dissolution of carbonates. The reaction kinetics here is written at the scale of the grain, and we have here the dependence of the kinetics. W2 is the mass fraction of the dissolution product. It's one other kinetics equation. It depends upon the specific area of the grain, which can be written as proportional to the inverse of the grain size. Here we've used an empirical law for the evolution of the grain size at a micro scale, inspired by the work of Paul Lade. So we have this simple relationship for the evolution of the specific surface with one material parameter, which is the grain crushability. Now, what we write here at the grain scale, we have to upscale it at the scale of the elementary volume. So this is this upscaling from micro to macro. And this is done by averaging the mass fraction of the dissolution product over the macro element here. So this is the averaging. And we do just to the second order Taylor development. So this naturally introduces the second gradient here, and with some material length, which is related to the size of the REV. So you see the characteristic size of the problem is actually the dominant wavelength of the heterogeneity of here the dissolution process. And when we go to the constitutive behavior at the macro scale, where we write a porosity-dependent yield surface, the porosity will evolve with the evolution of the chemical reaction. So at the end, going of the derivation, what we obtain is actually a non-local constitutive law, because here the hardening parameter, which is a chemical reaction progress, will depend on the second gradient of the evolution of the dissolution product. So this is how the yield surface is shrinking because of the increasing porosity or because of the development of the chemical reaction process. And we have applied this to the problem of injection of reactive fluid and looking at the possibility of compaction bending. And you see here how the strain localizes in small, narrow zones here. And the thickness of this zone depends on the crushability of the grain. So stronger crushability of the grain, slower permeability, faster reaction rate will lead to thinner compaction bands. So here again, you see the ingredient is to take into account the heterogeneity of the dissolution process, define the appropriate length scale for it, and this length scale will control the actual thickness of the localized zone when considering this injection of reactive fluid. So we have seen the combined effect of dissolution and cataclasis with positive feedback, multi-scale process, and how the heterogeneity of the dissolution process controls the spacing and the thickness of the compaction bands. With such an approach can be useful in application to CO2 storage. So I come to my conclusions. We have seen the new challenges in rock mechanics related to energy transition and climate change. I have illustrated some advanced experimental techniques combining testing and imaging, some new advances in modeling fracturing with efficient numerical tools, and we see that promising use of machine learning, multi-scale and multi-physics couplings, but still challenging issues, how to model all these coupled phenomena with evolution of the microstructure of the material through various mechanical and chemical process, and still the problem of cross-scaling couplings, how we consider different time scale and name scale for general problems is still a challenging issue. Thank you.